Okay, so hello everybody. Today I'm going to be talking a little bit about solid lubricants for spaceflight applications. So, what exactly is a solid lubricant? During my last tutorial, I previously discussed liquid lubricants, which are primarily used in order to reduce the coefficient of friction between two surfaces. This normally happens. Usually, we use liquid lubricants to make machine parts flow faster against each other. And what happens is that the asperities are separated by this liquid film layer, and the coefficient of friction is dependent on the viscosity. So you can see here the Streibeck curve, which I've included up here in the top right corner. It shows the regimes of friction um, given the Percy number, which is a function of viscosity and the sliding speed and the load of um, the load between the surfaces. But solid lubricants are different. They're actually materials that are able to reduce friction despite being solid. How does this happen? We'll talk a little bit more about it later, but it's actually preferred to have solid lubricants in certain applications where liquids can cause issues, such as in a vacuum environment, under high pressure environments, in applications where you have air flowing, such as pneumatic valves, and many other applications. Um, some of the benefits include that they do not evaporate when they're exposed to high temperatures, and they do not get they don't get squeezed out of interfaces when the loading pressure is too high. Whereas liquid lubricants may have that issue. So the solid lubricant that we're going to be discussing today is known as molybdenum disulfide. But in general, solid lubricants have this layered structure where they're covalently bonded in the plane, and there aren't any bonds connecting the two planes. So really, like graphite, if you're familiar, it's allotropic hexagonal carbon. Molybdenum disulfide is similar to this. It's covalently bonded in plane. There are no interactions between the layers. It's only van der Waals interactions between the two layers of molybdenum disulfide. So molybdenum disulfide works because the layers of the MOS2 will adhere to the two surfaces in contact, and instead of the asperities between the surfaces being the contact point, the surfaces of molybdenum disulfide can actually slide past each other. So the sliding coefficient of friction depends on the strength of the van der Waals interactions between two sliding planes of molybdenum disulfide. So up to our big topic today. Why does NASA use molybdenum disulfide? Well, the most commonly used solid lubricants today are graphite and molybdenum disulfide. Molybdenum disulfide operates much better in vacuum than in ambient air, which is ideal for spacecraft applications where you're going to be operating in a vacuum environment, presumably. Um, Molybdenum disulfide can operate up to at a temperature of up to 350 degrees Celsius in air, but up to about 1,000 degrees Celsius in vacuum, which is incredibly important, especially if you're going to be um, flying close to the sun in space, or if you're going to be sending lunar lander modules onto Venus or other planets where the atmosphere may be a lot hotter than it is here on Earth. And more importantly, it's also a very poor conductor of heat and electricity. Whereas if you compare this to graphite, it's effective in ambient air, only effective in ambient air because the adsorbed water from the air reduces the van der Waals interactions between the graphite layers, which makes it such a good um, lubricant. Without adsorbed water, the coefficient of friction of graphite is actually around zero point 0.8, believe it or not. And it's also a very good conductor of heat and electricity, which is not necessarily a good thing if you're going to be operating in such high temperature environments. So there are a couple of ways to apply molybdenum disulfide to a surface. The four primary methods are either rubbing it into the surface of a material, dipping it into a solvent with molybdenum disulfide, such as water or hexane, and allowing evaporation. You can use a binder material to bind the molybdenum disulfide to your surface, such as a ceramic like a silica material or some resin, or you can sputter it in a vacuum. NASA actually prefers vacuum sputtering. Why is this? Well, you can achieve a much thinner film using vacuum sputtering than through any of the other methods. You can get films on the order of nanometers thick. You can get it microns thick, and because you have so much control over the thickness of the vacuum sputtering film, it reduces the cost and the weight of the material. And additionally, you also will have higher compatibility with very precisely machined parts, where a lot of machine parts can be precise down to the micron. So if you want to apply some liquid or excuse me, some solid lubricant to a surface, adding a solid lubricant won't significantly increase or decrease the tolerances of these machine parts. So I've been talking a little bit about sputtering. What exactly is sputtering? Sputtering is a type of physical vapor deposition. So you can imagine that there's some vacuum chamber, and you're injecting an argon plasma inside this vacuum chamber. And inside this vacuum chamber, there are two surfaces. There is one surface of the material that you want to coat the substrate with, the substrate being um, uh, presumably the surface that you want to lubricate. So in our case, the target material will be molybdenum disulfide, and the substrate would be like stainless steel, for example. But what happens is the argon ions will collide with the target material, the molybdenum disulfide, and knock the atoms off into the vacuum, and they will experience a random bulk inside the vacuum chamber and eventually land onto the substrate. There's a magnetic field that confines the argon ions to continually collide with the target, increasing its momentum and confining it to this kind of circular area around the magnets, which you can see in this diagram here. So it can continually displace more target atoms. And this creates this atomic layer film of molybdenum disulfide on your substrate, which, for example, in NASA's case, is stainless steel. So, as you can probably imagine, molybdenum disulfide was, if they sputtered onto a stainless steel substrate using this magnetron sputtering machine, the sputtered molybdenum disulfide films are actually rarely stoichiometric. The sulfur to molybdenum ratio is actually not always 2. As you can see in these diagrams on the right side, there seems to be some kind of sputtering profile where you see like an average of maybe like 1.7 sulfur atoms for every molybdenum atom, and that changes as a function of the distance. So there were some films that were created in a NASA laboratory. There were some films that were created in a European laboratory, and they studied the effect of wear and tear, of cyclical usage, and studied the coefficient of friction of these films. So how do they actually measure the friction of like a lubricated surface? Well, there's this test known as the pin and disc tests, which measures friction on a surface. What happens is that you have a pin and you have a surface, and a circular surface, a disc, you could say. And in this experimental setup, both the pin and the surface are made of molybdenum disulfide. And if you do it in ultra high vacuum, you can spin the disc containing molybdenum disulfide on some kind of stainless steel substrate, and it makes contact with the pin under load. The disc rotates at a controlled rate, and the wear rates and the friction coefficients can be determined based on how much wear you see on the pin, for example. But yeah, they're usually made of the same material, but you can get a lot of useful information, such as the friction coefficient and wear rates out of this test. So when NASA actually tested this molybdenum disulfide sputtered film, they sputtered the molybdenum disulfide onto stainless steel discs. They tested 4 loading conditions. They tested about half a Newton, 1 Newton, 2 Newton, and around 3.6 Newtons. You can see this. You can see this here on the graph. But on the x-axis is how many times the disc was rotated, and on the y-axis is the observed coefficient of friction. What you'll see here is some interesting behavior where at first the coefficient of friction for the first couple of passes or the first couple of rotations is actually significantly high. But as you increase the number of rotations, it drops really low for a little bit until it eventually reaches a steady state. This is known as running in. It's a chemical reaction process, and usually the coefficient of friction which is reported is going to be the steady state coefficient of friction. But as you can see here, the coefficient of friction observed for the lowest load, the 0.5 newtons, is actually higher than the coefficient of friction observed for the highest load. And we'll get into this on the next within the next few slides. But there's also a lot of interesting frictional behavior in wear endurance. As you can see, this is essentially the same graph, except we extended this all the way to failure. So the coefficient of friction still is on the y-axis, but this time we see how many rotations it takes in order for the film to actually slide off of the material, and in order for the solid lubricant to stop working. So as the load increases, as you can see here, the number of cycles before failure decreased significantly. So for the lowest load, it was able to survive 40 times 10 to the 3. So what's that? 40,000 cycles. Whereas for the highest load, 3 newtons, it was only able to survive about 4,000 cycles before being slid off the surface. But yeah, we see here that the coefficient of friction is significantly lower for the greater load due to the standardized amount of electrostatic interactions between the layers of the molybdenum disulfide. So how is the friction coefficient affected by the load? Well, according to the Hertzian contact model, the coefficient of friction is equal to or proportional to the loading condition to the minus 1/3. This Hertzian model assumes spherical asperities, where increasing load increases the contact radius, which is proportional to the cube root of the loading. So as you can see here, the points on the graph here, we can see that for different regimes in the friction coefficient graphs that I showed you earlier, you can see that as you increase the amount of load, for example, this triangle here would be the 0.5, this would be the 1 Newton, 2 Newtons, 3 Newtons. As you increase the load, the friction coefficient decreases as proportional to the loading to the minus 1/3. And this is due to the Hertzian model. This is predicted by the Hertzian model, and it is confirmed by experimental data taken by NASA. So this is very interesting. As for the effects of pressure on the lubricity of molybdenum disulfide, we know that molybdenum disulfide is a very poor lubricant in air because it forms these corrosive products when it's exposed to oxygen. However, if you have very low concentrations of oxygen, it's interesting because the coefficient of friction can actually decrease as you increase the concentration of O2. So if you look at this graph here on the side, you'll see the partial pressure of oxygen on the x-axis. And it'll be increasing 10 to the minus 7 all the way on the left side and 10 to the minus 3 all the way on the right side. And the coefficient of friction that is observed is going to be on the y-axis. And as you can see, as you increase from 10 to the minus 7 to around 10 to the minus 5 partial pressure of oxygen, you'll actually see a significant decrease in the coefficient of friction. This is some interesting behavior. It's not exactly clear why this effect happens. It may be phenomenological. There are some theories that related to the adsorption and desorption of oxygen at the sliding interface. As for the effect of ambient temperature, the ambient and the temperature on the coefficient of friction, the pin on the disc sliding test that I described earlier, they were performed under 3 different ambient environments. For example, they performed the coefficient of friction testing, the pin on disc testing in air, they performed it in vacuum, and they performed it under nitrogen. And they also tested all 3 conditions at 5 different temperatures. They tested it at 0 degrees Celsius, 100 degrees Celsius, all the way up to 400 degrees Celsius at 100 degrees Celsius intervals. And you can see this here in this graph on the right side, where the circles depict the coefficient of friction experience at each temperature under vacuum. The squares depict air, and the triangles depict nitrogen. And as you can see, there isn't a significant relationship between the temperature and the coefficient of friction, but the ambient is extremely important. As you can see, the nitrogen is actually the best ambient environment for molybdenum disulfide to work as a lubricant, whereas vacuum is better than air. And air is the worst ambient environment for it to work in because it forms these corrosive products, which we mentioned earlier. So where does this bring us? Why is all this important? Well, in the 1960s, in the late 1960s, NASA started their space program, and in 1969, NASA sent Apollo 11 to the moon. So we know that temperatures on the moon can reach 120 degrees Celsius during the day. This is way too hot for liquid lubricants. For example, water boils at 100 degrees Celsius. Other liquid lubricants have even lower boiling points. So if they were going to be exposed to the high temperatures on the moon, the liquid lubricants would easily evaporate, and we would not be able to, the parts on the Apollo 11 lunar lander would experience significant wear and tear. And this is obviously not desirable. So there are other and also there are other factors too. The vacuum pressure on the moon, for example, is 10 to the minus 10 pascals, which is way too low for liquid lubricant or graphite, because graphite needs H2O in order for the H2O to adsorb onto the layers of graphite to reduce the electrostatic interactions between the layers. And it's also way too low for liquid lubricant because, as you can imagine, some liquid lubricant would become gaseous in this kind of environment. But the legs of the lunar lander were designed to be retractable. They wanted the legs of the lunar lander to be retracted into the body of the lunar lander while they were in space flight. Only needed to be extended upon landing on the lunar surface. So with these factors in mind, considering everything that we've discussed already so far, NASA chose to lubricate the leg joints of the lander with molybdenum disulfide in the 1960s, and that's what all this research was for. They wanted to study how molybdenum disulfide operated under vacuum conditions. They wanted to study how it operated under different temperature conditions. They wanted to see how the wear and tear of the molybdenum disulfide would possibly affect the performance of the substrates that it would be lubricating. And after all considerations, they decided to go with molybdenum disulfide. And we have molybdenum disulfide to thank for successfully bringing our men to the moon and giving us all this important scientific information that we take for granted today. So that's the end of my talk. Thank you for listening, and I look forward to answering any questions that you may have. Thank you.